Hi, I'm Michael Killin, and I head a project that has the goal of helping the public, the world, whatever, identify the most deadly threat of climate change. And then also, part of the project is to help those organizations that have a solution be heard, share their message with the world. First of all, I believe the most deadly threat of climate change is the melting of the ice in the Arctic, the Antarctic, in the Alps, the Himalayas, and places in Africa and other places. The ice is melting faster than ever every single day, and if we don't find a way to stop it, it will have a profound effect on civilization. Now, I believe that there are hundreds and thousands of different solutions that are being promoted to try to slow or stop climate change. I believe there are 4 that are really critical. And one is a tax on carbon. Another is education. Try to increase the critical thinking of the people in the world to understand what's going on and what they can do about it. Nuclear energy and renewable energy. Those are the 4 solutions that my team is trying to help suppliers, governments be heard, and to develop support or sales or whatever for those particular solutions. On this show, I've invited an associate of mine. He's been on my show more times than I'd like to think. He is Alex Cannara. He is an expert on nuclear energy issues, developments, products, services, whatever. I'm going to ask him a series of questions about a new type of reactor. They're called small modular reactors. I believe when these products really come out on the marketplace, they can have a significant impact on slowing climate change. Alex,
thank you.
Thank you.
Glad to be here.
I hope you don't feel like you're a victim.
It depends on what happens.
Yeah, I know. I get a little pushy sometimes. Alex, but would you first put small modular reactors in terms of the wattage, the watts they would you put that in perspective with the traditional large?
Right. Well, a traditional nuclear power plant, first of all, has 2 reactors, so that when one is being refueled or some maintenance work, the other one is still running, keeping the external society powered up. Those have generally been large reactors, large enough to run about 1 million homes each. So a power plant like Indian Point or Diablo Canyon can power about 2 million homes, or equivalent in terms of industrial output. And the output of each of those large reactors is about a little over 1 billion watts. So that sounds like a lot, and it is. 1 billion watts of energy is a lot. Electrical power. So what unfortunately has happened over the years is that the research that was done in the 60s on smaller versions of reactors for power plants kind of got sidetracked. Obviously, the Navy uses small reactors to power its warships, like aircraft carriers and submarines. And that size of reactor is pretty much ideal for powering things like a large industry or a community of homes and businesses in the order of about 200 to 300, 400 megawatts, million watts. So a fraction of the 1 billion watt standard reactor for large power plants.
So are you saying what's on the reactor on an aircraft carrier, a submarine, that would be a small modular reactor? Would that be correct?
Yes, in the common terms we think of in terms of modular, because the reactor can be removed when the ship needs to have its nuclear fuel replaced. It can be removed as a unit and replaced with a unit that's already fueled up and ready to go.
Good. As you were talking, I got this idea about safety. What is more dangerous, having a nuclear reactor on an aircraft carrier, or that carrier going near a hostile country?
Well, given the missile technology today, I think we'd want to keep the carrier away, quite far away, and protected from that kind of threat.
So, you know, if the federal government, the French government, other governments put nuclear reactors in the military ships, and you cannot have failure there because everybody is gone. So,
the reactors will, the reactor in a ship is designed particularly so that it has very great safety, but it's designed to run for 30 years without refueling, roughly. So that's why they're different from our commercial reactors, because the fuel they use is really a weapons-grade fuel, and we don't use that legally in commercial reactors.
Okay, so there's no waste.
So that, well, the waste, every 30 years, the government takes out the used fuel and reprocesses it or stores it and until it's safe to be around. So the point of those reactors is something that we should be thinking of in general, is that the Navy doesn't want to have to refuel a ship very often. They used to have to go and stop at a port somewhere to get coal or oil to refuel, which exposes them to the danger you mentioned earlier of some hostile power. So you don't want them to be in port for 30 years if you can do it, and that's what we can do basically with current submarine and aircraft reactors.
Okay, for many years we've had these gigantic reactors, 50 years maybe?
Well, 60 at least.
60, and every year, every day, the suppliers and the users of them keep trying to make them safer and safer.
Well, they are safer. There's nothing as safe as nuclear power that's regulated. You can go through all the accidents that have happened, and you can say, well, that Chernobyl, that reactor was illegal everywhere outside the Soviet Union. So there are regulations to prevent that kind of reactor and end the accident from occurring. So that's irrelevant to nuclear power safety in the United States or England or China. So what you've got then is a series of performance issues. For instance, in one of the first reactor accident we had in the United States was at 3 Mile Island in Pennsylvania. And what happened there was a mistaken operating indication. The operators weren't trained to actually handle all the possible ramifications of what failed, some valve issue in the plant. And so they had a partial meltdown of the core. It got too hot. But no one was hurt, nothing was released, and everything was fine. The problem that was there in front of us was that the utility companies who owned power plants, nuclear power plants, weren't working together to train their staffs on safety and just general operation, how to do it. And as a result, the uptime, the time that they were actually running a nuclear plant in those days, was like 65%. That means that a third of the time the reactors weren't running, generating clean electricity. After 3 Mile Island, there was a push to form inter-industry organizations that would oversee training and operation and so forth. And there's one called WANO, another one called INPO. Those organizations brought all our nuclear operations from 65% uptime to 90%, which is what they are today. So imagine how much coal in the east, remember this is Pennsylvania, was prevented from being burned and much pollution because we simply made operation better. And that's the key to anything, but it's why nuclear power that's regulated is the safest.
Okay, this is the start of a new decade, and I have a feeling in this decade there is going to be a greater yell, scream for help in slowing climate change. I mean, more and more people are going to realize not only their homes, their property, their jobs, their finances are going to be adversely, but even their lives. Okay, and now, starting in this decade, it seems there's more discussion or starting up about these small modular reactors.
Right.
And I noticed the other day in France, one of the great organizations of France, Electricity
De France.
of France, announced a new small modular reactor. They call it the New Wood, the New Wood. And let's see, they got great partners. They've got the Navy, the French Navy. They got this organization called CEA, Technique Atomica, and then they even have a partnership with Westinghouse.
Right.
Tell me what you think of Newwood.
Well, it sounds to me from what you've told me and what I've looked up, that they're building a version of a kind of a standard power reactor that Westinghouse, for instance, has made over the years. What's called a pressurized water reactor, which is like a pressure cooker that gets hot because you have uranium or other fissionable material in the reactor that fissions, releases heat, and basically heats water, and then you can make steam from that hot water to run a turbine and get power from a generator, or if you're trying to make a submarine, turn the propeller. So that their design seems to be very sensible shrinking of the technology that we've had for 60 years in big power plants, and adding features that would make it essentially impossible to have it cause any damage outside itself. So that it would shut down automatically, and it would not be a problem getting too hot because of that, and so forth. So I think their ideas are quite good, and they're related to the other small modular reactor companies that are working currently, like Terrestrial Energy, Thorcon, and so forth.
What's related to them?
Well,
we're talking about Newwood,
right.
but what was the connection to these others?
Right. The connection is that you have something that is small enough in power, heating, that you can use it for a good logical purpose, like running a factory or a mining operation or something of that, or like we do with a ship. I mean, that's what they've been doing with their designs and what we do with our designs for shipboard reactors. But you can do it in such a way that if you want to build a power plant that has a certain amount of power output, then you might need only one of these, or two of these, or three of these. But at any time in the future, you can make it bigger or smaller,
Okay.
right?
Good.
So that's the whole idea of the modular part of the name. And the modular really has to do with the logical construction of a plant and how it's managed. It really doesn't depend upon the technology inside the reactor, how it's making its heat.
Okay. Now, Jan van der Lee is the vice president for global nuclear development at Electricity de France. And I asked him for a few thoughts about Newwood, because I think it's an important product, especially when a gigantic corporation like Electricity de France teams up with Westinghouse. We might have something. This is what he wrote. The market for SMRs, small modular reactors, are mainly replacement of coal plants, which are typically of the size of hundreds of megawatts. Other markets are remote and coal areas where small modular reactors can replace coal or diesel, providing electricity and heat. Canada, remote areas in South America, mining industry, and others are applications for Newwood and other small modular reactors. He goes on to say, we are negotiating now with potential customers, and he points out we're also working very closely with Westinghouse. So from what he just said, would you like to add anything?
Well, I mean, I think that's a very sensible way to proceed because, in fact, the first commercial power plant in the United States at Shippingport, Pennsylvania, was equivalent to what the power output of one of these small modular reactors is. It was 60 megawatts, so it's not even 100 megawatts, and yet they're talking about their modular reactors, just like other companies are talking about 100 to 300 megawatts.
Yeah. Can you tell what kind of fuel NuWid uses, liquid or solid?
Well, it sounds to me from the description that they're using solid conventional nuclear reactor fuel, which is 5% fissile fuel and 95% plain old uranium from the rocks, which is kind of like water and milk. The milk solids that our bodies need are a very small fraction of what you get when you buy a gallon of milk. The rest of it's water. So fuel for commercial reactors is really very diluted. And that's why I'm bringing that up, simply because that's one of the reasons why it's very safe for us to use in commercial reactors.
Okay, I'd like to ask about another small modular reactor. How about the company NuScale? They're in Portland, Oregon, in the United States. You familiar with NuScale?
Yes, somewhat. I mean, they're doing a similar kind of thing in the sense that they're taking a solid uranium-fueled reactor design using heating water to make steam to generate electricity through a turbine, for instance, and they're scaling it down in size so that it is not only more appropriate to lower demand purposes, like, as you say, like for mining operations or even a desalination plant. I mean, our desalination plant down in Carlsbad, California, takes about 40 megawatts. So that's a little less than the smallest reactor we've built for commercial use, right? So that would make some sense to use it for that. But NuScale is designing basically a standard reactor design, but small enough so that they can fit a variety of purposes and can be multiplied in a bigger power plant. So you could install several of them if you needed more power. But they're safe and self-contained, and there's no way for them to run away and get too hot and melt down.
It seems to me almost the entire thing is built in a factory.
Yes.
And then it's delivered. And sometimes that's good it's built in a factory because there's a lot of economies of scale, and you can control a lot of that. Okay.
Well, these are all, because they would be for commercial purposes, they would all be regulated carefully in design before they even were built. And then once the design is approved and the construction is being designed, that has to get approved too. And then how they get transported and installed and operated in their location that they're going to end up in, that all has to be approved. So that's an important thing about modularity.
And it seems NuScale, a competitive feature that they're promoting is that, look, we build basically the whole thing, and that means when we install it, it goes in really inexpensively. You don't have to, create the whole thing. What about Moltex Energy?
Yeah, Moltex in UK.
Yeah.
They've switched now. They are now in a different realm in terms of the fuel. So we have conventional solid fuel that heats up water to make steam. That's what we've got so far, everything you've mentioned. They're using molten salt. And the reason you use molten salt is because, unlike water, molten salt becomes liquid at maybe 400 degrees centigrade, but you can heat it up much hotter than you can heat water, up to maybe 1,000 degrees centigrade. So now you have a very large temperature range that you can have in a reactor, which makes it more thermally efficient. So it can generate more energy from the same amount of fuel. So that's one of the reasons Moltex exists. And there are several others that are doing that kind of thing. Thorcon is one, Terrestrial Energy in Canada is another. That salt use makes the heat engine that's generating your power more efficient. And that's one of the big advantages. The other advantage is that molten salt can be drained from the reactor quickly if there's something wrong. So now the salt can be just dumped into some storage tanks underground if there's something wrong within the reactor very quickly. And we did that research at Oak Ridge National Labs in the 1960s. We had a reactor making power this way. It operated for 17,000 hours. And when we shut it down in 1969, same year that we landed on the moon, the salt was dumped into underground containers, and it's still there.
So the molten salt is designed to give us more flexibility over the use of water.
Yes.
Let's say at 0 degrees, it's freezing, I guess. I forget now.
Well, yeah, 0 degrees centigrade is freezing for water, and 100 degrees for boiling.
And the molten salt allows us to work with water over a much higher range.
Yeah, you have to melt it, so it's about 400 degrees centigrade, and then you can go all the way up to above 1,000 degrees centigrade.
It's like something the engineers and scientists like to take advantage of.
It's red hot.
It's red hot. Okay.
The whole reactor would be red hot.
Now, I asked the CEO of Moltex. He is Stefan Heighton, okay, to make a comment. And what I like is, like the Electricity de France folks and some others of the small molten reactors, they are addressing the need to do something about climate change. So Stefan wrote this: overall, the technology is capable of having a huge and perhaps unique impact on climate change. I like to hear that.
Yeah, well, if you get more power because you have a bigger thermal range, that's less size, less materials. You're more efficient in terms of generating power, but also you don't need to have quite the same, let's say, expanse of land or whatever is needed for a power plant if you've got these small machines, small modular machines. And as I said, the use of salt means that the machine can be turned off very quickly, very simply, if there's some issue.
Okay, what about terrestrial energy? I think they're in Toronto, Canada.
Yes, they're going through now approval with the Canadian government for their design, so they're well ahead of most of the other molten salt companies. And our NRC has actually agreed, amazingly enough, to work with the Canadian regulator to approve at the same time, which means that we're actually going to get something done in the United States, which we haven't been able to do for years, about advanced reactors. It's very nice. The other thing to be sure that people understand is that when you use something like a molten salt, which is a very stable chemical item, you have huge safety benefits that arise from that you no longer have to worry about things like melting down of solid fuel because it's all molten already, right? All you have to do is store it somewhere if you want to, if you think something's wrong. Yeah.
I've noticed that, what has it been, a decade or 10, 15 years, the suppliers have been building small modular reactors, and they're still, well, maybe with the NUID, well, let's just say they're still not on the market.
Well, again, certification of a design, which is why nuclear power is safer than anything else, including solar panels. I mean, they're not certified for their environmental safety at all. I mean, that's put it. We can go through that, and that's another topic. But the point is, the regulation is for nuclear more strict than for anything else, and so we would never be doing the same things, regulatory things, for other forms of power because the commercial markets wouldn't like it. But the point is that nuclear power has always been, from the beginning of its commercial nature, highly regulated, and therefore it's very safe. Safer than putting up solar panels on the roof. Even Fukushima demonstrated safety because it was not regulated properly. So if it had been regulated properly, it never would have had the accident that it had.
So getting certified is something that really takes, it's very important, but takes a long, 10 years?
Well, I think that we are smarter nowadays about doing it, and I think the small modular reactor business embodies that smartness so that we can move much faster to build small modular reactor designs, get them approved, than we've done in the past with the larger systems. Not that the larger reactors are anything to get rid of, and they're important. We depend on nuclear reactors of the gigawatt size.
Okay.
There were about 440 of those running around the world last night while we were asleep. They're still running. They're going to run tomorrow. They're going to run next month, next year. All those large reactors are very carefully regulated and operated.
Are you enthusiastic that these small nuclear reactors will take off exponentially, probably?
I think certainly in the rest of the world, the way EDF is planning to do, the way other companies are planning, terrestrial energy, they're all planning, and they're working with potential partners, and so they know that the market is there and will expand quickly. I mean, Thor Conference is working with Indonesia. Indonesia would rather sell its gas and have a nuclear plant, or 10 nuclear plants, or whatever. And so the small modular reactor can actually make that happen.
Selling gas.
Well,
is that
okay, so here's the economics. Canada wants to have nuclear small modular reactors so that they can exploit, yes, so they can exploit they can reduce the carbon footprint of their oil shale exploitation. Think about that for a minute. But that's the only way you're going to get a new nuclear reactor into an oil field and replace some of the burning, right?
Alex Cannara, thank you very much for being a guest.
You're welcome.
And I always learn a lot from you, and I plan to learn more from you in the future. I'm Michael Killin. Thank you very much.